So we were actually last time in this course, actually, especially in the ISM part, there are two aspects. One is the microphysics, the quantum mechanics and the actual physical processes at small scales which are happening. You have to be very careful about what they are, right? The other is what are the implications of it on macro things like the temperature of a nebula, size of the Stromgren sphere, and so on. They're extremely tightly coupled. But the macrophysics is governed by microphysics. All these atomic parameters affect the things like macroscopic things like the size of the H2 regions and so on. So yeah, so both aspects are actually important. In this course, we are actually not doing a lot of atomic physics calculations. A lot of these information is available as tables that you just simply use. But it's important to be aware of what they are based on. Okay. Okay. Right. So, so let me actually quickly again recall. So you have a O or a B star which has a temperature larger than 20-30,000 Kelvin. It produces a lot of photons which have h nu greater than 13.6 eV. These photons can ionize hydrogen, and if you wait for recombination time, it creates this ionized bubble around the star, and this is called an H2 region. Now, outside the H2 region, the gas is taken to be neutral. Inside it, it's almost fully ionized. It's not totally fully ionized because it's in steady state at all points. So the rate at which ionization is balanced locally by the rate at which recombination is happening. So even inside here, there are neutral hydrogen atoms. If they were not there, you won't have photoionization, right? If you don't have neutral hydrogen there, if only inside the H2 region you have only protons and electrons, you only have recombination. You don't have photoionization. So there is a very small density of neutral hydrogen even within the H2 region. The other thing that we talked about was this on-the-spot approximation or case B reionization, case B recombination, in which what we say is that if you have hydrogen, effectively all these recombination which happen from a free electron going to this n equal to 1 level, these photons have a very short mean free path. And they are actually absorbed right within this H2 region by these neutral hydrogen atoms which are there, because they have their cross sections are very high, right? Because they'll immediately ionize this neutral hydrogen. The other thing that is involved in case B is that all these recombinations, right? So not recombinations, this is transitions. These are bound transitions. All such transitions from some higher n to n equal to 1, which will produce Lyman series photons, they are also immediately absorbed because in fact their cross section is even higher, because so it will sort of produce a line photon, and there are these neutral hydrogen atoms within here. They will absorb this photon immediately. Okay, so effectively in this optically thick case to Lyman continuum photons, right? So it's optically thick to Lyman continuum photons. All the Lyman continuum photons produced within the H2 regions because of recombination to n equal to 1 will be absorbed locally on the spot. So it's as if these recombinations never quite happen because they are almost immediately reversed by uh, ionization or by this. So if you have line photon emission, it is just immediately absorbed and the photon goes back to higher n value. So that's why you can just ignore the n equal to 1 transitions, and that's the case B approximation. In lower density nebulae, case A can apply. That is, there the optical, uh, the optical depth can be small for Lyman continuum photons, and in that case, as soon as a Lyman continuum photon is born, it can just leave the system. But even in those cases, the line transitions to n equal to 1, say n equal to 4 or n equal to 3 to n equal to 1, they can still be optically thick because the line cross section is much higher than the continuum recombination cross section. Okay. So all these this is all consequence of these atomic physics, and you have to be mindful of all this. Okay, because it has consequences. Okay. So we just dealt with the hydrogen last time, but there's also helium. By number, helium is about 10% of hydrogen. Helium has a higher ionization potential. So helium-1 has an ionization potential which is 24.6 eV. Okay, and helium-2 has an ionization potential. So helium with single electron, which is hydrogen-like ion. So this the energy levels and everything for this guy is known absolutely nicely, right? Because a single, it's a hydrogen atom with Z equal to 2. So this is 54.4 eV ionization potential. Now, for typical stars, even most massive stars don't produce such hard photons. They don't produce photons higher than 54 eV typically. So helium is either helium is either neutral in He1 state or in He2 state. If it's a massive star and the temperature is high, you can have photons which have energies higher than 24.6 eV. Okay. So in this case, we have to actually also be very careful about the atomic physics. These numbers are absolutely important, right? Because the photoionization cross section is 0 below the ionization potential, and as you cross the ionization potential, it sort of is high and sort of falls like a power law, like nu to the -3 or something. Okay. So what if you have helium? What complications can be there? So I'll not be doing the mathematics of it, but I'll just tell you the idea. So so here I will actually need my slides. Okay. Right. So let's actually go to that point. So yeah, these are, say, some photoionization cross sections for different ions and molecules and so on. So this one is hydrogen. This one. No. This one is hydrogen. Okay, this. And this cuts off at 13.6 eV. So below 13.6 eV, sigma photoionization is 0. And sort of it peaks here and sort of falls off like nu to the -3. This, there is like a atomic physics formula, exact formula for hydrogen, but all of them have more or less the same behavior, right? There is a step function and then a power law drop. And for helium, you can see this one. So this is neutral helium. The ionization potential is 24.6 eV. So, it picks up there. Now, what is this? This is H2, hydrogen molecule. It gets ionized at slightly higher energy compared to neutral hydrogen. So here are other abundant atoms. So this is carbon. Notice that the carbon ionization potential is lower than hydrogen. What it means is that in an H2 region, carbon will be fully ionized. Because if you can ionize hydrogen, you will definitely ionize any carbon atom that you encounter. So carbon will be fully ionized. The oxygen, coincidentally, has almost the same ionization potential as hydrogen. So, but hydrogen is more abundant. So hydrogen gets preferential treatment when it comes to ionization. So, you know, this coincidence has a lot of interesting implications. And you can actually see these edges because these are multi-electron systems, carbon, oxygen, neutral carbon, oxygen. So they have like other uh, electrons can be kicked out, right? The first at higher energies, sometimes you can hit a resonance of an inner electron rather than the most loosely bound electron and so on. So
These values are calculated.
yes, these are from atomic physics calculations. Um, so here again, there are others. So carbon, oxygen, hydrogen are pretty common. Carbon and oxygen are the most abundant after hydrogen and helium. Then this is singly. This is for neutral carbon. This is photoionization cross section for neutral carbon. Or otherwise, it would say C2 or whatever. Uh, higher probability of oxygen getting ionized. But there's also abundance, right? So it is N times sigma. So N for hydrogen is higher. Okay. So these are for other ions, which are also quite important ions. So similarly, Mg has an ionization potential which is below the hydrogen ionization potential. So Mg will also be ionized in an H2 region. In fact, uh, in fact, not just ionized in the H2 region. So even photons with energy less than 13.6 eV, continuum photons with energy less than 13.6 eV will leak out of H2 region, right? Uh, but line photons will not, right? So they will be absorbed immediately inside. But there is a large frequency or wavelength space where photons will come out. These photons will ionize the nearby neutral regions as well. So carbon, silicon, magnesium, even in H1 region, in normal neutral regions, are mostly ionized because of this, because they get ionized at below 13.6, and those continuum photons can come out of H2 regions. So a lot of neutral ISM has carbon in ionized form, silicon in singly ionized form, and magnesium in singly ionized form. Okay. Um, right. So it's just, uh, yes, that's what I'm saying here. Okay. Now, ionization and recombination, the atomic physics of this is actually quite, I mean, there are a lot of things through which ionization and recombination can happen. Okay. In H2 regions, we talked about photoionization and radiative recombination. Right? Those are the dominant processes, but there is a bunch of different processes which can ionize gas in different places. So, you have photoelectric absorption, which is what happens in H2 regions. You can have OJ effect, OJ ionization. So you can kick out, like if you have a hard photon, it can kick out an inner shell electron, say in iron, and uh, it creates vacancy. So the electrons come down, but it can eject more than one electron, it can kick out. So this is called the OJ effect. So then you can have collisional ionization. at high densities. So these are like the micro steps of these kinds of processes, which you have to be aware of. But in certain places, one of these or two of these will dominate. So you don't have to bother about all of them. But it's important to realize that there are various ways in which atoms can get ionized and atoms can recombine. So these are these are the recombination processes. Um, this is radiative recombination, right? What happens in H2 regions is this. But then you can have dielectronic recombination. It's sort of like the opposite of OJ effect. You have two electrons involved in this. So so you have an ion and you have an electron. The ion recombines with this electron, but this ion gets excited at a very you know active state or some sort of a resonant state, and it can it can excite. In this excited states, you can have two electrons or more than two electrons which are in the excited state, and one of those two can have a de-excitation and produce a photon. So these are some of these processes. Now there are various things happening. So there are these, as I mentioned, there's ionization happening, there's recombination happening. Both these reactions are happening all the time. If the rate of these processes is fast compared to the age of the system, then such sort of chemical reactions will reach equilibrium. The rate of forward reaction and the rate of backward reaction are equal. So you can actually think about various types of equilibria, right? So you can have ionization equilibrium, in which ionization and recombination balance each other out. You can have thermal equilibrium, between heating processes and the cooling processes. For example, in H2 regions, there is heating happening because the photons are producing photoelectrons, right? And these photoelectrons, which are sort of kicked out, the bound electrons which have been made free, carry extra energy, right? More than the ionization potential. That energy is carried in thermal motion. So every ionization production of photoelectron produces this kinetic energy, which is thermalized in the H2 region. So it heats the H2 region. Similarly, you have cooling. You can have collisions can excite lines of, say, oxygen or nitrogen, uh, which have transition energies which are less than 13.6 eV. So those excited states will radiatively decay and produce a photon which can leave the H2 region because its energy is less than 13.6 eV. So, or you can have free emission. You can have recombination radiation, right? You have excited, you have ionized a hydrogen atom. These electrons can go to, say, n equal to 5 level. They recombine to n equal to 5, but then they can go from 5 to 4, 4 to 3, 3 to 2, and in these steps produce recombination radiation. Okay, and this recombination radiation photons just leave the system. So that's an energy loss for the system. So this is about thermal equilibrium, and then there is chemical equilibrium, right? Between different chemical reactions. For example, in the cold interstellar medium, there are molecules forming and breaking all the time. So you can have an equilibrium between chemical reactions. Similarly, uh, we have collisional equilibrium, right? The electrons, protons, ions are all different species are colliding, and they're trying to reach Maxwell-Boltzmann distribution function. So this idea of equilibrium is extremely powerful, and it applies in general to all such reversible microphysical processes. Okay. So people who are online can actually ask questions if they have, or if they are still there. Okay, let's see.
We do you mean by ionization equilibrium? Like, so basically, if the star is still producing photons that can ionize the.
Yes, in H2 region it is, right?
So ionization should be more.
No, that's no. It will reach it's sort of like um, uh, right. If you have like rabbits and fox in a closed system, it will not never have zero rabbits because fox will die as soon as you have zero rabbits. In the same way, you cannot have like so in that sense, it reaches equilibrium in the sense that the rate at which foxes eat uh, rabbits is the same as the rate at which rabbits reproduce. Some sort. So equilibrium is so even though there is this massive star which is ionizing hydrogen, but it is producing proton and electron. They are all ready to recombine. Right.
Basically, ionization.
So if,
the rate of ionization remains the same, the rate of recombination increases.
Right, absolutely. It's like chemical equilibrium, right? So the equilibrium is reached at different conditions, but equilibrium is reached if you have a reversible process. Okay. I'll actually go through this. Right. So in actually Drain's book, for example, you'll find all these tables. Right. So these are actually very, very useful. These are from papers, and these give you like various approximations for recombination to 1s state. Right. So what is alpha? Recombination coefficient to the state 1s. This is recombination coefficient for recombination into 2s, 2p. So this is alpha 2 is the sum of these two. Right? Because, these are all the recombination happening to into n equal to 2 and so on. So I've just sort of shown it. So if you sum up all these alphas, you get alpha A, right? Alpha A includes even n equal to 1 recombination. But if you subtract this guy out, you'll get alpha B. So you can actually see the difference between these two is this, because you are ignoring recombination to 1 n equal to 1 state. And these are calculated at different temperatures, which are sort of relevant to H2 regions. And there are these approximations and whatnot. Now, there's also a little bit of atomic physics involved here. So these are energy level diagrams for the hydrogen atom, right? So this is 1s, 2s, 2p, 3s, 3p, 3d, and so on. And suppose you have what are the possible allowed transitions, not forbidden. Allowed transitions have delta small l equal to 1, right? So there is a change in L. So for example, if you have an electron in 4D state, it can easily go to 2p state. Delta L is 1. Similarly, a 2p photon can easily go to 1s photon. But 2s photon to 1s cannot happen. It's a forbidden transition because delta L is 0. So what happens in that? So why I am telling you all this is because the end result of all these recombinations is that all these 2s and 2p are connected to all the other states through some sort of allowed transitions or another. So eventually, all these things will radiatively recombine very quickly to the 2s and 2p state. And the 2p state can very quickly go to 1s state. But the 2s state is somewhat longer lived, and uh, it does not decay to 1s through a simple line emission. There is a 2-photon continuum emission. So there are 2 photons released for 2s to 1s transition. And instead of producing a single line, it produces a continuum. It produces a spectrum. Okay? Because there are 2 photons produced. So it's sort of a, by energy conservation, your energy is not fixed. Though that energy can be split between 2 photons. And there's like a continuum. So the energy can go from 0 to full Lyman alpha energy. But there's a continuum instead of a line. 2s to 1s transition is a forbidden transition because delta L is 0. And it happens through a 2-photon emission. So that's atomic physics. Okay. And what it means by 2-photon emission is that instead, so normally if you have one electron in n equal to 2 and n equal to 1, the transition happens and this energy difference, which is this produces 1 photon, right? Which is 1216 angstrom, the Lyman alpha transition, 2p to 1s is that. But this 2s to 1s is not a delta function in frequency. Since it produces 2 photons, the 2 photons can have, like, it can have Lyman alpha by 2 energy. Instead of Lyman alpha energy, it can have half-half. It can have 3/4, 1/4, and so on. So it produces a continuum instead of a line. I think so. I really don't know the atomic physics of it, but it's important. It's important for this because of this produces a characteristic spectrum. This 2-photon process. Okay. Okay. So what you can actually, even this time scale to go from 2s to 1s is not that long. It happens on, so this happens like on 10 to the -4 to 10 to the -8 seconds. The allowed transition happen very fast, but this happens on 10 seconds, which is still very small. So this happens. 10 seconds is large, but it's small compared to the recombination time. The 10 to the 4, 10, 10, yeah, 10 to the 3 years. Now this is neutral so this is helium. So it's the same diagram that was done here. So hydrogen diagram everyone knows. This is the same diagram for helium. So helium has 2 electrons. This is for neutral helium. So it has 2 set of energy levels. One is the triplet state. So if your 2 electron spins add up, so you have s equal to 1, and you have the 2 electron spins are in the opposite direction, and that's the singlet state. So this is the singlet state energy levels. This is the triplet state energy levels. There are no transitions across these. They are forbidden transitions. So the singlet to triplet or vice versa does not happen. So it's only within this or within this. Okay. And so in the same way here as here there are different transitions which are shown. Here also delta L equal to 1 is the allowed transition. So these are all allowed transitions. Okay, so 1s 3p to 1s 2s and 1s 3d to 1s 2p and so on. So in neutral hydrogen also the same story holds, that everything comes down to 1s 2p and 1s 2s and 1s 2p and 1s 2s. You have these singlet. The spin can be 0 or 1 by probability of their spin degeneracy. So if spin is 0, degeneracy is 1. If spin is 1, it's 2s plus 1, so 3. So 1:3 ratio, you'll have atoms in this and this state. Okay. Now, that's right. So this is a forbidden transition. So what happens is all the helium, once it sort of recombines very quickly. So the Einstein A's are very large. So they just, things come down to this 1s 2p and 1s 2s states. And the 2p state can immediately come down to the ground states. But this takes some time and it happens through 2-photon. Even here, the atomic physics is the same, that this is a forbidden transition. It happens through a 2-photon process. Now this 1s 2s triplet to a singlet transition, so this is at a higher energy. This also happens, and it happens with a small value of A. This is a forbidden transition. And what you can actually see is that, so this is 625.56 angstrom. This is less, this is less than 912 angstrom. So this is basically will be immediately absorbed by hydrogen, right? And also it can be absorbed by, uh, by helium itself. So these transitions, this is also at 584.33 angstrom. These can ionize neutral hydrogen. Okay. So in the detailed calculations, you have to be mindful of all this. And the people who who work on this for research, can actually do all these calculations. They can produce which lines and what continuum spectrum and so on will be produced from H2 regions. The key thing to notice is that pay attention to the energies of these transitions. 13.6 is an important number. 24.6 is an important number. 54.4 is an important number, because these are ionization potentials for these common atoms. Yeah, so that book has a lot of atomic physics tables. And so once these sort of once you have recombination radiation, this is sort of the intensity of line ratios. So H alpha to H beta at 5000 Kelvin, this is the expected line ratio at 5000 Kelvin. If it is just simple recombination, you just populate the high levels and it's sort of just coming down. So so as you increase the temperature, this ratio becomes smaller, because H beta is more accessible. Those n equal to, so beta is 4. So n equal to 4 is more populated at higher temperatures compared to at lower temperatures. So these tables are there, and that's what astro people would use. They won't do in principle the atomic physics calculations. Similarly, there are these recombination rate coefficients and tables of that. Okay, let me skip this. Okay. I will talk about this. Okay, so this is actually also, these are all tables from Drain's book. This is a table of different massive stars, O stars. So this is their spectral type. This is their mass. This is their effective temperature, number of hydrogen ionizing photons produced per unit time. Q1 is the, right, so Q1 by Q naught. So Q1 is the rate of emission of H nu greater than 24.6 eV photons. Why do we care about this value? This can ionize helium and also hydrogen. So that's why this is important. And this is the total luminosity. And you can actually see as you go to O9.5, the Q1 by Q0 ratio becomes smaller, because these are cooler stars. And if you go to cooler temperatures, the black body will have less and less very high energy photons. I mean, this is nothing. This is the same data plotted as a figure rather than in the table. So if you have this is Q1 by Q0 versus effective temperature. Okay, so this will come back here. Okay. So so when we have helium involved, so we have to actually be careful. So for helium as well, case B conditions hold, right? Because helium is only 1/10 the abundance of hydrogen, so it's fairly abundant, and all recombinations to the singlet 1s state give rise to photons which are immediately absorbed, except say a 503 angstrom photon or something, which is absorbed by hydrogen or or a continuum photon, which is absorbed by hydrogen and not by helium. If you have a continuum photon, which is produced by recombination, so suppose uh, a free electron recombines to the ground state of hydrogen, it will produce whatever, more than 24.6 eV. If it is absorbed by helium, of course, then it's as if this recombination never happened. But if it is absorbed by hydrogen, it's not the same thing. It's not as if this recombination never happened, because it's not like it's not it's affecting the population of the ground state of helium, because by being absorbed not by helium but by hydrogen. So all these considerations you have to be careful when you include hydrogen, when you include helium and other metals. If you have other metals in there, their abundances are so small that it really does not matter. For example, they don't really contribute a lot of you know they won't contribute a lot of recombination photons as much as hydrogen and helium. So they don't really matter all that much for the structure of H2 regions. But they do matter for other aspects, specifically uh, cooling and heating aspects. Metals are very efficient coolants of H2 regions. So let me actually first tell you how metals cool the H2 region. So so there are metals like oxygen. So in astronomy, we call everything which is not hydrogen and helium metal. So for things like oxygen and nitrogen, uh, they have excited state. So they are ionized because in H2 regions, nitrogen and oxygen are ionized. Not fully ionized, but they have 1 or 2 electrons removed, depending on the temperature of the central star. And what happens is collisions, like electrons can collide, and if they have energy transitions which are at an energy delta E, which is less than 13.6 eV, the recombination of that or the downward transition will produce a photon which is lower energy than 13.6. So it will immediately escape, taking away its energy. That's why metals are very important, but because they provide these pathways for cooling of the H2 region. Okay. So now we'll do a little bit about cooling and heating of H2 regions. Right. So actually, H2 regions can also have dust, and dust can have important implications, right? If you have dust in the H2 region, uh, it can absorb the ionizing photons, so it can reduce Q naught. So it can actually reduce the size of your Stromgen sphere. Uh, Dust can also affect the thermodynamics. It can produce photoelectrons, and it can heat the H2 region. So we will not be doing dust in H2 regions, but it's important to be mindful of it. The modeling of H2 regions is actually extremely sophisticated, and it's very important to produce diagnostics for these systems. Okay. Dust are, dust are like particles. They are, uh, I mean, it's sort of like they are micron-sized particles. They are not like single molecules. Uh, they are coagulated particles, and uh, so you have to treat them differently. It has very complex chemistry as well, very complex radiative transfer. So the temperature of H2 regions is close to 10 to the 4 Kelvin, right? That we have already mentioned. But the exact temperature, whether it's 5,000 Kelvin or 20,000 Kelvin, depends on the balance between cooling processes and heating processes, basically thermal equilibrium. Okay, so let's see. So let's look at X plus R plus H nu. This gives you, this is basically photoionization plus R plus 1 plus electron plus kinetic energy, right? This photon has more than the ionization potential energy of X plus R. It produces an electron, and that excess energy, H nu minus ionization potential, which is equal to H nu minus H nu naught. So H nu naught is ionization potential. That energy is essentially with the electron or the atoms. The lower mass guy carries most energy in such reactions. So this is called photoheating. Photoheating. The electron carrying the energy produced due to photoionization. So you have X plus R plus 1 plus electron. So this is recombination. So this has some kinetic energy. Will produce X plus R plus H nu. And if this H nu is less than 13.6 eV, or if it is not exactly resonant with something else, it will just leave the H2 region, right? Carrying away essentially the the kinetic energy of this electron, right? Is all radiated away. So this is a cooling process. So let's actually define some things. So let's see. So this is zeta X plus R. This is probability per unit time for photoionization. Zeta X plus R. This is equal to nu naught to infinity sigma PE. Sigma PE is that photoelectric cross section for photoionization. Nu times C times U nu by H nu times d nu. But U nu by H nu is the number of photons per unit volume from frequency nu to nu plus d nu. This is just, and so it's sort of like n gamma, n nu, right? So this is number density of photons. So n nu d nu is number density of photons from nu to nu plus d nu. So number density times sigma times C is nothing but rate. And so, and for nu less than nu naught, sigma is 0. So it's only from nu naught. So this is right. And I've actually not multiplied this by n X plus R, right? So this is probability. So for a given X plus R ion, what is the probability per time that it gets photoionized, which is this. Okay. So n X plus R times zeta X plus R, this is rate per unit volume, right? So this is a number of photoionizations per unit time per unit volume. This gamma PE, or the heating rate per unit volume due to photoelectric heating, is equal to n times x plus r times nu naught to infinity sigma pe nu times c times u nu by h nu. It's the same expression. Now I'm actually writing energy rather than just the probability. So you'll have h nu minus h nu naught, right? This is the energy. This is the energy that's produced. That's with the photoelectron, right? Which it sort of thermalizes with the rest of the plasma through collisions. So this is the heating rate per unit volume due to photoelectric effect or due to ionization. This is ionization uh, heating rate. Photoionization heating rate, actually. So ionization heating rate. Right. And at all times, we are assuming ionization equilibrium, right? The rate of ionization equals rate of recombination. So what it means is uh, zeta c, this zeta x plus r times n times x plus r is equal to alpha. This is the recombination coefficient ne times x, nx, not x. So this is just uh, ionization equilibrium. So in ionization equilibrium, number of all ions, number of electrons, everything is fixed in time. So this is the rate of forward reaction, the backward reaction. So this was probability per unit time. This is number density. So it's rate per unit volume. Similarly, this is recombination rate. So this is ionization rate per unit volume. This is recombination rate per unit volume. Your sigma, this gamma PE, the photoelectric heating rate or the photoionization heating rate, say from H to H plus by photoionizing hydrogen, this is about alpha B, case B recombination, right? So what we are doing, so yeah, just a sec. So this would be, just a second. Before writing this in terms of the recombination coefficient, let me write it in terms of this is equal to this is equal to n h plus times, sorry, not h plus, n h times say theta h, right? So basically, this is the rate at which no, so this is just the rate, right? This is n times xi, n times zeta is just the rate per unit volume. But you have to multiply this by some energy. So what you can actually do is say, okay, psi times k t c. Psi, this KTC is the color temperature of the star. So this is basically uh, the energy of the photon that's coming from the star, central star. This psi is a factor which sort of defines like So this whole thing is average energy of the photoelectron, right? So psi, it can be, yeah, it can be a stellar type and of the star type as well. Uh, Basically, this is average energy of photoelectron, and if you divide it by the sort of kT of the radiation field to which this is exposed, you get some sort of a dimensionless. This psi, this is a dimensionless. This is a dimensionless parameter, which just quantifies the average energy of the photoelectron in the H2 region to the average energy of the photon coming from the star. Psi is order unity, but yeah, go ahead. Yes, yes. Exactly. And that is also the reason that this psi is less than 1. Right? Because not all the energy of the photon is in the photoelectron. Some of it is lost in ionization. So all the atomic physics basically goes in psi. Okay. So for a precise calculation, of course, you should also include photoelectric heating of the helium atom, ions and so on. But this is reasonably good because hydrogen being most abundant. Okay. So you can have additional heating mechanisms. So for example, you can have photoelectrons. So the dust can absorb uh, photons which are like between 10 to 13.6 eV. Right? So these are the photons which are not so much sought after by neutral hydrogen, which is so abundant. These can be absorbed by the dust, and it can produce photoelectron. The similar kind of thing can actually happen, right? Uh, so the detailed calculations are actually quite cumbersome, but the ideas are sort of reasonably simple. Okay. There are also other heating processes. For example, if you have cosmic rays, cosmic ray particles can come and hit the nucleons there. You can have Coulomb interactions, and they can heat the gas. They can lose their energy and heat the gas. You can have MHD waves which can dissipate and heat this plasma and so on. But they are all subdominant compared to photoelectric heating in an H2 region. What about cooling processes? Cooling. So the uh, first is recombination radiation. So what is recombination radiation? Uh, so an electron with some kinetic energy recombines, and that energy produces a photon. That photon leaves the system, and that's an energy loss. It cools the system. Okay. Uh, so let's see. Let's call it lambda RR. Right. So this lambda is cooling rate per unit volume due to radiative recombination. This is equal to alpha B. Right? So you only take alpha B into account because n equal to 1 recombinations are as if they never quite happened because they don't really lead to the loss, escape of photons. So alpha B times Ne times NH plus. So alpha B Ne NH plus is just the recombination rate per unit volume, and then what we need is average energy lost due to radiative recombination. So this is average kinetic energy lost in radiative recombination. So this sigma, the cross section for radiative recombination as a function of energy, is sort of a power law in energy, sigma naught E by E naught to the gamma. And now, so basically, recombination is sort of a collisional process, right? You have an electron and an ion colliding and recombining. So what you have to do is to calculate the rate coefficient. So sigma V radiative recombination, you just have to do this, right? That sigma V times integral 4 pi V squared e to the minus E by kt times dV, right? This, these we have encountered, some time ago. And when you have collisional processes, you actually average over the Maxwell distribution over velocities. And if you average over all the energies, and if you take some sort of a form like this, you get a power law in temperature. I mean, that's the only thing you can get. There's some sort of a power law. All these are, E naught, sigma naught, and so on are atomic physics, right? Collision physics. So we'll not get into that, but we have this expression. And ERR, the energy in radiative average energy in radiative recombination that's produced is about is equal to 2 plus gamma times kT. T is the thermal temperature, the temperature of the H2 region. Not TC. TC was the temperature of the star, the color temperature of the star. Yeah, because here we are taking it as a Maxwell Boltzmann distribution of velocity, so T has to be the gas temperature. Okay. You can actually calculate this value of gamma from your atomic physics. As I said, you have alpha, you have you have expressions for alpha B as a function of temperature, right? So alpha B is sort of very similar to this guy. So the temperature dependence of alpha B and gamma are related. And I actually showed you these tables of alpha B and the functional form. There was like a temperature dependence, some sort of a fit which had a temperature dependence. So you can actually read off gamma from just comparing that expression, for example. But the upshot is ERR value, if you do that exercise, it's about 0.7 to 0.8, depending on whether it's A or B, right? So if it is 0.7 to 0.6 actually. So this is for case A, this is for case B. Case B has to be lower, right? Because some of that energy is not lost. Whereas in case A, even the one transition to 1s is that energy is lost. So it has to be higher times the kT. So basically, what does it say? In the same way as we quantified this psi, the dimensionless average energy of a photoelectron relative to the color temperature of the star, this is the average energy that the photoelectron loses because of average energy that the plasma loses because of radiative recombination as a function of the plasma temperature. So, right, the energy of the of an electron is 3 by 2 kT, but on average, it loses per recombination, it loses 0.7 to 0.6 to 0.7 of that. Just but just about half the energy it loses in recombination. Not all of it, because at high energies the cross section goes down. So those recombinations are not that efficient. So only at lowest energies the recombinations are more predominant. So the average is dominated by the lower energy part. Anyway, so this is the first cooling process, radiative recombination. So, right, so you'll have a free electron with some kinetic energy, and it is going to recombine to this level, and it sort of is going to produce a continuum photon. Um, right. And then this also actually includes this transition, right? So this will produce, say, n equal to 5 to n equal to 4. That's also recombination cascade. And then this one, of course, will not produce a photon because it's n equal to 1, which will be just immediately absorbed. Right. The underlying assumption is that very quickly all the hydrogen atoms, neutral hydrogen atoms, very quickly decay to the ground state, n equal to 1 state. So there aren't a lot of hydrogen in n equal to 2 state. So if you have 3 to 2 transition, there isn't a lot of hydrogen with n equal to 2 which can immediately absorb it. So it is just escapes. Okay. So this is about recombination radiation. What about? I mean, the photon has an energy h nu, right? Yeah.
So, like kinetic energy of photoelectric.
Hmm?
Kinetic energy of the photoelectron, that is also lost.
Right. So the energy is it produces a continuum photon. So ionization potential plus that energy. Uh, right. Yes. So the second thing is free emission. Free emission. So if you have a if you have a plasma, it emits due to free emission. So you have, you have electrons and protons and electrons and ions zipping past each other. That process accelerates the electrons and makes them radiate through free emission. Pay attention to that the microscopics of these different processes are different. Free emission does not involve any sort of atomic transitions. It's like a purely classical way of producing radiation. Right? It's by accelerating electrons. Accelerating charges produce radiation. So free emission. So this is so lambda free. Uh, so this you can actually derive, uh, is equal to, 1.4 times 10 to the minus 25 erg per centimeter cube per second. And then there is some quantum correction, which is small, so I'll just ignore it. So there's 1 here, 1 plus something, which is small. And then T4 to the 1/2 ZI squared NE and R. And so all these radiation processes are two-body processes, right? Electron and ion come together and collide to produce Bremsstrahlung or free emission. So this is how it goes, like, so it's n squared. Similarly, this one is also NE and I, right? Whereas photoionization is not NE and I inherently, but in equilibrium, in ionization equilibrium, this is nothing but alpha NE n x plus R plus 1. So this also becomes n squared, because in equilibrium, recombination and ionization balance each other. So this also becomes n squared. Okay, so this is free emission. And if you normalize it to the case B recombination rate, so alpha B Ne NH plus, right? This is equal to 0.54 T4 to 0.37. By plugging in alpha B's dependence on temperature is what you're getting. So this times KT. Right, so this is just energy. This ratio is energy because this is energy per unit volume per unit time. This is number of recombinations per unit volume per unit time. So, so at higher temperatures, for example, uh, lambda FF sort of increases relative to just KT. So, here again, we also had this, right? We took KT out. What fraction of KT does the plasma lose because of recombination? So these sort of are comparable. You can see this is 0.7, 0.6 times KT, and this is also about the same. Okay, so then the third process, and the most important process, is collisionally excited line emission. I already mentioned this. So here, what you have is metal lines, oxygen lines, nitrogen lines, sulfur lines. Those, so you have electrons colliding with these ions, they'll excite them, and as soon as they're excited, they get de-excited and produce photons, which have energy less than 13.6 eV, and that can actually escape because there are no other resonances. I mean, if you do the same thing for hydrogen from n equal to 1, there are resonances, everything is will be absorbed. But for these ions, they are not as abundant. So these photons, and also they're not, neither are they, their abundance is like 10 to the minus 4 times hydrogen. So a lot of this radiation will not excite other atoms in ground state. Okay, so let's see. So ion, so for example, you can have oxygen 1, oxygen 2, oxygen 3 can occur in H2 regions. So this is lambda C, collisional excitation. So lambda due to collisional excitation is equal to summation over x, summation over I, n x comma I times summation j less than I times aij ei minus ej. So let me tell you what I'm writing here. So you have some, some energy levels. So this is energy level J. This is some energy level I. EI minus EJ is this energy difference. Okay. And this will produce a photon. AIJ is Einstein A for that transition. So probability per unit time that this decay will happen. NXI is the number density of ion X in energy state I. Right? So this is the number density of this ion X in energy state I. So if there are these lower states than that, you can have decay from here to here, here to here. And if all these have lower energies than 13.6 eV, these can just escape. And this can cause a lot of cooling of the H2 nebula. H2 regions are sometimes also called nebulae, right? A lot of these are like Orion nebulae, are like the most famous nebulae. So this is probability per time. This is energy difference. So this is number per unit volume. So you have energy per unit volume per unit time that is produced due to collisional excitation of these metal ions, metal lines. Okay, so I have actually talked about heating processes, cooling processes, and now the temperature of the H2 region is determined by the thermal equilibrium between these two processes. So, and that thermal equilibrium is reached at a certain temperature, right? Because both heating processes are proportional to Ne times N proton. Because, we related it to recombination. Similarly, these things are also proportional to right, but the photoelect, the radiative recombinations are also making it lose energy. No, it's not. It is. That's what I'm saying. The equilibrium, as long as these time scales for heating and cooling are short compared to the age of the system will reach equilibrium. So in thermal equilibrium, what happens? You have gamma PE, the photoionization heating is equal to total lambda, total cooling. So these are heating rate per unit volume per unit time, or heating per unit volume per unit time, which is heating rate per unit volume. This is cooling rate per unit volume. This is equal to lambda CE, collisional excitation of these metal lines, plus the radiative recombination of hydrogen, plus lambda FF, the free emission. Now this is the dominant cooling component, dominant. Okay. And this is what will determine your temperature. So, some of the common cooling species are nitrogen too. And in fact, a lot of these, most of these transitions are forbidden transitions. The major coolants are forbidden metal lines like N2, O2. I'll actually show in the slides. Neon 2. All these occur in H2 regions. Right? They are singly ionized species, S2, S3. I'm not like marking the transitions here, but just mentioning the ions. So these are some of the transitions. I mean, these are just some of the ions which provide a lot of cooling. I have not mentioned the transitions, so that's why putting these brackets does not really make sense here. But let me actually immediately go to. Oh, it's much higher. So I'll actually show you quantitative things now. So in fact, this is what it is. So thermal equilibrium determines temperature distribution in an H2 region. Okay. Now, so here this is gamma PE, this photoelectric heating per unit volume per unit time as a function of temperature, right? So we had written it down. This was alpha B NH NE times psi KTC, right? So this is for an Orion nebula type condition. So you have stars which are like 35,000 Kelvin. So this is gamma PE. This is heating rate per unit volume. This is free emissivity. So free emission per unit time, energy per unit time per unit volume. This is due to free. Okay, it sort of slowly increases the temperature. This is cooling due to radiative recombination. Now this is due to collisional excitation. So you can actually see it's almost like a factor of 5 more than these guys. Okay, and this is for abundances in Orion. So these things will depend on abundances, right? If you don't have any metals, you cannot excite metal lines. So this will come down if your metallicity is not there. And this is the sum of all three pathways: the collisional excitation of metals, which produces forbidden lines, radiative recombination, and the free emission as a function of temperature. So at higher temperatures, you have more and more radiation, right? And that sort of makes sense as well, because at higher temperature, the electron has a higher energy, and when it recombines, it produces, higher energy continuum photon. Mm. Or there are uh, more metal atoms or metal ions which in the higher state. So they are all like easily and they undergo many more uh, downward transitions and produce photons and lose thermal energy. So this is where the equilibrium is reached, right? Where these two, so this is sort of a one zone model in a sense that you're considering the whole H2 region to have the same temperature, right? And same heating and cooling, which is sort of okay. The temperature variation is not huge. So this is the point at which the photoelectric heating balances the radiative recombination and the collisional plus the free cooling, about 8,000 Kelvin. So, so this gamma PE decreases with temperature, lambda increases with temperature. Why does gamma decrease with temperature? That comes from alpha B. The recombination coefficient decreases with temperature, if you recall, t to the minus a half or minus 0.8 or something. So, so that's why it sort of decreases. Now, if we break down this lambda CE into various ions, this is how it looks like. So this is contribution due to oxygen 3. This is contribution due to sulfur 3. This particular transition. And if you add them all up, you get this lambda CE, right? You can always do that because this loss is happening due to these specific transitions. So you can actually see a major coolant of H2 regions is actually this O3 forbidden line at 4960 angstrom. And all these other sulfur 3 lines and whatnot. So these are the forbidden fine structure metal lines, which are the major coolants of H2 regions. Now, this is for Orion conditions. Now, let's see. This has 0.1 times the abundance of Orion. Metallicity has been reduced by a factor of 10. So this lambda CE comes down, right? Lambda C is proportional to the abundance of ions, Nx, you remember. So if it becomes 0.1 times that, so this comes down. And gamma PE more or less remains the same. So the curves cross if you bring this down, the curves will cross at a higher temperature, right? And that's what is happening. The equilibrium temperature in this case is about 16,000 Kelvin as compared to 8,000 Kelvin in the previous case. Okay. And that's just because the lambda CE has been suppressed. This is if you increase the abundance to 3 times the Orion value. Here, the equilibrium is reached at 5,400 Kelvin, lower temperature. Simple. I mean, this is actually reasonably easy to understand. What about higher densities? If you increase the densities, what happens in that case? So, if you increase the densities, what happens is you have these radiative de-excitations of metals, say, right? So you have O3, and there is some transition which produces a photon. If your density is higher, some of these de-excitations happen through collisions rather than through emission of photons. And if you have de-excitation through collisions, no energy is lost because no photon is produced. So you can see as you increase the density, you are reducing the cooling rate because no photons are produced in that case. So that's what is happening. So with increasing density, the equilibrium is reached at a higher temperature. These remain the same, right? So cooling rate as normalized by NHNE remain the same, but the uh, CE, lambda CE decreases because of this contribution due to collisional de-excitations, which does not produce photons, which can leave the system. Okay, so this is okay. So I'll actually show some images here. So this is an all-sky H alpha map for Milky Way, and it shows bright regions in H alpha, n equal to 3 to 2 transition. So this is radiative recombination line. Right? 3 to 2 is a radiative recombination line. And you can actually see a lot of these things are H2, these things are H2 regions. Okay. This is the Orion Nebula. So this is an H2 region, which is sort of excited by massive stars here. I mean, of course, this is not spherical because the density structure in the interstellar medium is crazy. And if you look at the central parts here, this is how it looks like. This is in N2. I told you, N2 and O3 are some of the major coolants of H2 regions. These photons are easily escaping out. Similarly, H alpha, H beta are easily escaping out because they have less than 13.6 eV, and there's no ground state to higher level. Right. So sometimes what happens is if you have a lot of stars and if you have supernovae and so on, you can blow out chimneys. You can actually carve out empty regions, low density regions in the interstellar medium, as shown here. So this is the sun. These are some molecular clouds. These contours are CO contours, shows molecular clouds. And this white stuff shows these chimneys. These are ionization bubbles. So what happens is ionization photons can leave through those regions rather than through the dense regions, because the the Stromgren sphere size is smaller. But in these other directions where the density is low, they can just essentially uh, what do you say, run through the whole of the ISM. So if your Stromgren radius is larger than the ISM scale height, then the photons can just fill the whole space beyond the ISM, because they are no longer encountering neutral hydrogen to ionize. They can form these ionization cones and chimneys.
The size scale of
Right. So it's about 100 parsec. If you can blow supernovae and create these uh, holes which are bigger than 100 parsec, and if you have young stars there, a lot of radiations from that star can actually go through this direction. So this is how Lyman continuum photons escape from star forming regions, right? You need to ionize the universe, and for that you require that radiation is coming from galaxies. So some of these ionizing photons have to leave the ISM and enter the IgM to ionize the IgM, right? So this is called escape of Lyman continuum photons from the interstellar medium. This I already showed. This I already showed. Okay. Right. So the last part today will be nebular diagnostics. So nebular diagnostics. Now you want to know the density and temperature and metallicity of these H2 regions, right? So, these are nebular basically means at 10 to the 4 Kelvin, close to 10 to the 4 Kelvin, which is photoionized gas, right? So what are some of the, say, for example, these metal lines? Can some of those be used to tell us about the metallicity of the H2 region or the density or temperature of the H2 regions? And the answer is yes. You want to use some sort of line ratios. So you choose some line, say N2, some line, N2, some line. You want to choose the same ion and different lines in that same ion, so that there are no problems due to relative abundance of different different metals in a particular region. So for example, to measure abundance, one thing can actually be O2, some O2 line to H alpha line, right? H alpha line, quantifies the abundance of hydrogen. O2 quantifies the abundance of uh, metals. So, some sort of a line ratio like this can be an indicator of metals. Okay, but you also have to be careful, because if their uh, if their energy levels are too far separated, then for example, if they gap if the H alpha transition is much lower energy than O2 transition, then you may not have O2 because of temperature, not because of abundance of oxygen. So you have to be like very careful in choice of your different uh, uh, transitions, metal line ratio, different line ratios, in order to use them as diagnostics. So let's see. So for temperature diagnostics, what do you want? So what should be the criterion? So of course, the energy gap of the transition should of course be less than 13.6 eV. If it is not, that line will not come out. Then the thing is, your energy gap between these U and IL, upper and lower levels, should be smaller or comparable to KT, right? The temperature of the nebula. Uh, if the energy gap is much larger than KT, then that that transition will never happen, because there will be no ions in the higher state. Uh, so in this case, both levels are collisionally uh, accessible. These should be abundant ions, right? If they should be abundant. If they are not abundant, then the strength of the line will be weak. And they should be collisionally excited, right? So this is actually related to what we were just talking about, this thermal balance in H2 region, right? If they are collisionally excited and then they get radiatively de-excited, then you have this line produced nicely. Okay. So what about the density diagnostic? What do we want in a density diagnostic? The energy difference should be very, very low. If the energy difference is very, very low, then e to the minus e by kt factor is not that important. If they are almost at the same temperature, if the energy difference is the same, the Boltzmann factor does not penalize one to the other. Um, so closely spaced. in energy. Right. Right. And what you want to do is uh, at low density, the line ratio should have some value, and at high density, the line ratio has some value. And so, if the density is high, what you have is uh, the line strength gets decreased for the same reason that you don't have collisional de-excitation. You don't have radiative de-excitation, but collisional de-excitation that reduces the line strength. Okay, so let's see. So for the temperature diagnostic, a common ion to look at for temperature is ions with NP2 configuration, right? So for example, so they have 2 electrons in P subshell. So for example, you have N2, singly ionized nitrogen, or doubly ionized oxygen. These are NP2, right? So oxygen will just have, so it will have 2s2 2p2, right? This kind of a configuration state. So if you look at the right, so these 2 electrons, you have to like draw uh, the fine structure levels. Okay, and that's sort of atomic physics. That's again something that we will not be doing at all. So there are like there is this LS coupling scheme which tells us how to create these levels, and there are these then they also have to satisfy the Pauli exclusion principle and all that. And once you do all that, follow the atomic physics rules, you can actually create these energy levels. And for this 2p2 or np2 state, the energy levels sort of look like this one. 2, 3. This is 0, 1, 2. These are energy levels. So 0, 1, 2. So this is 3p0 state. This is 3p1 state. 3p2. So these are term symbols, right? So it's 2s plus 1 lj. This is how you have these 2 electrons. So you have to do S1 plus S2 to get capital S. So you have to do L1 plus L2 vectorially to get this capital L, and similarly L plus S to get J. I'm not going to do that. Okay, but so this is what these are what you'll get as your the fine structure, levels. So this is a triplet state. So S equal to 1, and then there is third excited state. This is 1d2. Right, so this is L equal to 2. L equal to 1 is P state. This is S equal to 0. And then you have 1 S0. And these are sort of the energy orderings as well. I mean, there are reasons for this. Now, let me actually mark some transitions. So these are all forbidden transitions. So this is 1. This is on the that the energy gap between these, states is small. So let me just mark. So this is 5756 angstrom. This transition is 5756, and this is 6585, and so 6550, and they also have, there is an E by KT for these levels. What is the energy? So this is at zero energy. This is 370 E by KT, uh, E by K. So this is the temperature, energy difference expressed in terms of temperature. So 370, uh, or 370, 70, 180, 22037, and 47,000. So basically, this is the energy gap. So this is a, a distribution of energy levels which has delta E, which is which is not very high compared to the range of temperatures that you have in H2 region. So both this line and this line will be emitted. So this is for N. This is for N2, and the same levels will be there for O3, because they have NP2 configuration, but the energy values will be different. Let's see. So this is the fourth level. So these are the transitions that we are going to look at. P4 to 3, right, is equal to E43. So N0. So let me actually write down first and then tell you what. C04 times A43 by A43 plus A41. So assume that all the N2 is in this zero state. Okay, and then you have collisions. So you will have collisional excitation from 0 to 4th level. Collisions will take an electron from 0 to this 4th level. This is the rate. This is the number density. This is the rate coefficient. So this is the collisional excitation rate. E43 is this energy difference between 4 and 3 level. This 5756 angstrom. So this is basically the line emission. This one, 5756. The intensity of that is proportional to the collisional excitation from ground to this times A43 by A41. Because A43 shows this one and A41 shows this one, right? So, the fourth level can either go to third level or to first level. This is a branching ratio. So what about P32? So we are going to use the line ratio, this line, intensity of this line to intensity of 32, this line. We are going to use this as a diagnostic for temperature. So P32 is equal to E32 times N0 C03. This is the same, the collisional excitation from 0 to 3 plus N0 C04. Right? So it can actually also get excited to the third level, this guy, right? So times A43 by A43 plus A41. Right? This is just the this level can actually be excited by collisions from here to here, but they can also be excited by this transition times. Now, if you are in the third state, you can have either this transition or this transition. Only allowed transitions are marked. Only, like, not allowed. These are also forbidden, but only like possible. I mean, if they are even more forbidden than this, they are negligible. Times A32, right? A32 plus A31. Right? So these are the, this is what uh, the line emission will be proportional to. This one. This is because this level can be populated not only by collision, but also by this transition. Right? So if you take this ratio, the emissivity ratio J4 to 3, right? J3 to 2, this is equal to A43 E43. I'm just sort of taking that ratio and simplifying by A32 E32 A32 plus A31. These are all like atomic physics parameters which we know. Times omega 03. Right. So there's this C03 and C04 can be expressed in terms of omegas. These are these collision strengths, dimensionless values. That's A43 omega 04 times e to the minus E43 by kT. E to the minus E43 by kT. Right, so this C04 right, so C0 right, so collisional coefficient from state 0 to 4 is proportional to e to the minus e by kT, the Boltzmann factor. This we did a little bit when we were doing collisions and the detailed balance. So there's a relation between this and this that involves this Boltzmann factor. But the upshot is now we have this expression for J4 to 3 to J3 to 2 as a function of temperature, right? We can actually plug in. So this is all atomic physics. These are also, and omegas are also well known. So now you can actually see at different temperatures, how does this line ratio go, and try to make this sort of diagnostic, temperature diagnostic. So this assumes that we are in a low density regime. So your Ne electron number density is much less than the critical density. So there's this idea of critical density, which says that if if you are at a density which is higher than this critical density, the radiative de-excitation becomes equal to collisional de-excitation. So your photon production gets suppressed if you are at densities higher than the critical density. So we are assuming here that all the de-excitations are radiative, right? In these, we have not we have not included uh, collisional de-excitations, right? We have not suppressed it due to collisional de-excitation. Okay. And that's actually true for these lines. The critical density is like 10 to the 5, 10 to the 7 particles per cc, which is much higher than typical densities that you encounter. So this is about temperature diagnostics. For the density diagnostics, so I don't really have much time. I'll just tell you the idea. So you need very closely separated uh, levels in energy, and then you look at transitions like this, and this, right? And the idea is at low densities, uh, at low densities, you are limited by collisional excitation. If your density is very low, uh, you're just waiting for collisional excitation to happen, and as soon as the collisional excitation happens, de-excitation will happen because Einstein A is pretty big. Okay, so that happens at low densities. At high densities, your level populations are Maxwell-Boltzmann. So at low density, so let's just mark this as uh, 0, 1, 2, and let's look at J 2, 0 by J 1, 0. So in this case, this is, at low densities, this is this is omega 2, 0 by omega 1, 0. These are collisional excitation strengths, E20 by E10. But they are very, very similar. E10 and E20 are very, very similar. And similarly, e to the minus E21 by KT. And I just sort of plugged in the temperature and energy dependence of this collisional excitation rate at small densities, at low densities. This is what happens. So this is just 1, and this is just 1, 2. So this is omega 20 by omega 10 at low densities. At high densities, what happens? At high densities, J 2 to 0 by J 1 to 0 is basically G2 by G. Basically, it's thermalized. These levels are all thermalized. And then in that case, it's just e to the minus E21 by KT times E20 A20 by E10 A10. And this is approximately G2 A20 by G1 A10. So you see, at low density and at high density, we have different expression for the line ratios. So this can actually be used as a diagnostic for density. So now my writing is done. Let me just show you in this slides. So this is the temperature diagnostic that I was talking about. This is N2, this is O3. These are the energy levels drawn properly. These are NP2 states, and these are the energy states obtained after LS coupling. So you see there are 3 P states and 1 D and 1 S state. So the arrangement is the same, right? You can actually see there are 3 here, 1 here, 1 here. The energy values are different because that depends on what type of nucleus do you have. Now this is an illustration of using these two as temperature diagnostics. So this is N2, these two line ratios, 675. This ratio, this to this one and this one, 6585. 6585 and that. So x-axis is temperature. This is line ratio at different densities. You can actually see if you can measure this line ratio it provides a decent proxy. So if you measure the y-axis, you can get x-axis. Similar, this is for O3, a similar line ratio. This is the temperature diagnostic. These are the
density also.
That's right. But you see, the dependence on density is weak. The 2, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5. Like 3 orders of magnitude, and the line ratio is only changed by a factor of 3, 4. So you need to have like a temperature diagnostic and the density diagnostic simultaneously. You should be able to solve it. These are O2. So that was O3 and N2 for temperature diagnostic. These are NP3 type levels. So these are the level diagrams. And you see these two states are very close in their energy. So this is energy in terms of Kelvin. You see they are almost equal. So 38604, 38575. Their energy gap is much less than KT. So this satisfies that thing that I worked out very quickly at the end. So here is the application of this O2 transition applied to nebula. The other thing that you have to keep in mind is it's not just n that the collisional cross section depends on. There is also a t to the minus 1/2 dependence. So that's why it's written as n times t to the minus 1/2. But recall, the temperature in the nebula goes from 5,000 to 20,000 Kelvin. It is not a very large range, whereas the density can have a much larger range. So you can essentially ignore this, but this is strictly what you will have. Now, when you are in the low density limit, right, it was just that omega 10 by omega 20 by omega 10 was the value that you got for the line ratio. Here you got that thermal value for the line ratio. So you can actually see if you are able to get the line ratio here, suppose it comes out to be here, you can actually get your density value. And the density values here are also in a reasonable range, like 100 to 1,000. So these are some of the lines that people use to infer the density of the nebula.
Yeah, the line ratio.
Oh, so the area under the line. So you have, just like we had the absorption equivalent width, you can measure the area under the line. So how much energy is coming in that line, and then just take that ratio. That's good. So that's what is called the line ratio. Now, not only can you use these transitions, these closely, so 2 to 0 and 1 to 0, you can also use the same uh, guys here, but then you can actually use these transitions. So 2 to 1 and 1 to 0. These are fine structure transitions. They come in infrared. The energy splitting is small. You can use this. So 2 to 1, this one. So 2 to 1 and 1 to 0 ratio provides a good density diagnostic for the same reason as what we talked about for the optical diagnostics, but they are in infrared and they're quite nice. And you can use the same N2 and O3 for this, because these are very small energy differences. If you do that, this is what you have. So you can actually see this is N2, the same species that we considered for the temperature diagnostic, but there we are looking at optical transitions. Here, these are infrared transitions. And this again, Ne to the T to the minus 1/2, for the same reason that at low densities, it's the collisions which excite, collisions are the rate limiting steps. At high densities, the level population should be thermal, and the two limits are different. And these are just calculations with all the atomic physics parameters put in at different densities and temperatures. So this is how you get. So I think we are done with H2 regions. So now the only there are two things remaining in this course. One is dust, and the other is a little bit about supernovae and the three-phase interstellar medium. Seather-Taylor and all that will not do the hydrodynamics of it, but why are supernovae important? Those aspects, the ISM aspects.